Well, thank you for coming to my presentation. A little bit about me. I graduated in mechanical engineer, and my first job was for NASA. And these are some of the projects that I worked on. That's the AX-5 spacesuit. That's not me in it. It could be me. She's not as tall as I am. And that's the Sophia infrared telescope that lands here in Christchurch occasionally. So after I worked for NASA, I moved into robotics. This is one of the robotic mining machines that we built for NASA. And that was a student project at my last university, which was a lot of fun. And from there, I moved into biomedical engineering, especially orthopaedics. So what you see here is a total hip replacement, for those of you that have had one or have had a relative that has had one. As a mechanical and biomedical engineer, I've spent many years at the interface between engineering and biology. Today, I'm delighted to have the opportunity to share with all of you what I've learned. So engineering involves so much more than providing a technical solution to a problem. It's a creative thing, and it can be quite beautiful. For instance, this building or this stairwell. Much of my career has been spent in the orthopedic industry, and I love the shapes of joint replacements with their delicate curves and the beautiful polished surfaces. But so much of what we do in this field is completely determined by the constraints of human anatomy. So we have few options on how we would modify things. When we design a knee implant, we have to work within these constraints. In other regions of the body, and as our knowledge has increased, our designs have also moved away from being geometric structures to being shapes or forms that are more organic and less geometric and machine-like in their appearance. This is some coral, and you can see how this implant for the skull has been inspired by nature and reminds us of other forms of life. In the past, we've used mechanical ways of solving problems, but we're moving into a new era of design, and one that looks to nature to solve engineering problems. So here's an example of the past, something that's easily visualized, washing windows on the outside of a skyscraper. So how many of you have seen something like one of these? They're ubiquitous, right? They're everywhere that you look. There are 90 cities globally with at least 10 buildings that are over 150 meters tall. This qualifies them as skyscrapers. And there are over 4,000 skyscrapers in the world, 4,000 of them. As an engineer, what I think is, that's a lot of glass. And we're going to need to tend that glass. So which city do you think has the most skyscrapers? New York. Any other guesses? Dubai. Vegas. You're on the wrong continent, folks. Hong Kong. New York City. Dubai. Shanghai. China comes up a lot. Tokyo. Shenzhen, Chicago, Chongqing, Guangzhou, Jakarta. We've got some Indonesia there, new country. Singapore. Put up Brisbane. I wanted to get a neighbor. Okay. So we had Brisbane tied for 72nd place with Manama, Bahrain, Philadelphia, Sao Paulo, Taichung, Tel Aviv, and Jian. There are more. So Brisbane has 13. There are other cities, such as Sydney and Melbourne, that have more. Not significantly more, but more. But they're our closest neighbor. And it's a beautiful city. This is Brisbane at sunset. We have a total of 5 structures over 150 meters high in New Zealand. And 3 of them don't count. One of them's the Sky Tower, and the other are chimneys from power stations. So that leaves the Vero Centre and the Metropolis, both of which are in Auckland. And there's the Sky Tower. Not a lot of glass on the Sky Tower, so it doesn't fit my example. And this is a daylight picture of the same thing. Again, that's the Metropolis, and that's the Vero Centre. And there's the chimney. We should be proud. We've got an entire nation, and 3 of our 5 skyscrapers are not skyscrapers. Okay. So window cleaning systems represent a superb feat of engineering. In the US, there has only been 1 death of a window washer in the recent 5-year period. We have developed a brilliant way to safely lower humans over the side of extremely high buildings, accounting for cable stretch, wind loading, slapping of the platform against the glass, and even the well-being of the people walking underneath. And yet it is slow work, as seen in this article from Curbed, New York. Cleaning the windows of Manhattan skyscrapers takes a long time. 1 day's work on an average drop takes around 4 hours, given good weather. It takes a month to clean the whole Hearst Tower from top to bottom. This is the Hearst Tower. Beautiful building. Work on larger skyscrapers in the city takes much longer. That's not a large skyscraper. A single cleaning cycle on the 80-story black glass curtain walls of the Time Warner Center, where the central canyon drop alone descends 700 feet, from the roof to the 4th floor setback, can take 6 men 4 months to clean. This is the Time Warner Center. So what comes to mind? For me, I say this sounds like a job for a robot and a good engineer, right? In fact, there are now tethered drones that can clean windows. And these drones are guided up from the ground and apply a jet spray of water to the windows. And they drag a hose with them, but even so, they can reach heights of 33.5 meters. Not exactly skyscraper level, but they're getting there. And the drones can clean windows faster than humans. So as you can see, there are many inventors out there working on robotic window washers. Drones like these with the mechanical design. These are just climbers, but we also have the drones. They can be used for firefighting with added thermal cameras and perform a lot of other functions besides washing windows. There's been some other innovative ideas in window climbing robots, and the version I'm about to show you was designed in China. 50%, imagine this, 50% of the skyscrapers built in 2017 were built in China. A window washing industry that now employs 400,000 workers just washing glass. That's a lot, like I said, it's a lot of glass. This robot that you'll see uses vacuum suction treads to transport the robot up the glass. It both scrubs and squeegees. The robot is equipped with around 150 sensors and 6 different types of propellers. And that's what it looks like. So it's 10 times faster than a human at cleaning windows. And although it's robust enough to withstand high winds, it's still limited by its geometry and by the skyscraper's facade. Did you see the problem that I saw with that video? Yeah. That robot in the video, it was not going to be able to step over any types of protrusions. And they very conveniently cut the video to a new scene every time it came to a ledge because it wouldn't make it. It wouldn't make it. So the question is, can we move away from traditional technologies and look to nature for inspiration? Hopefully the answer is yes, because that's the topic of my lecture, right? We can, by embracing a new field of engineering called biomimicry. It can be direct, like this robotic dog, or like the spy cockroach there that will scurry out and hide away from the light and record everything you say every time. Or it can be some type of synthetic fibers that act as a temporary skin for burns or other things. And over the centuries, nature has solved challenges in thousands of unique and robust ways. And we can use these same concepts and approaches to solve problems with man-made devices. So one of the challenges we have in orthopaedics is cartilage. It doesn't have a blood supply, so it doesn't grow back. Once it's worn away, it's gone. The same is true for the intervertebral discs in your spine and the meniscus in the knee. So everything we do in orthopedic design has to replace the joint or vertebrae with a man-made material. What I'm showing here is the meniscus. And one day, I learned that dogs can regrow their meniscus. What? This boggled my mind. Another mammal with very similar knee anatomy, this is a dog, can regrow a tissue that we can't. What enables it to do this? And how could we mimic this ability to help humans? By applying a discipline frequently referred to as tissue engineering. But the inspiration often comes directly from nature. Tissue engineering improves or replaces biological tissues by using biochemical and physiological factors. It studies how tissues are formed at the cellular level both in humans and in nature, and then attempts to replicate those properties, such as this organic material ear, or these intestinal lumens that are growing in situ. I love the golden ratio. I've borrowed some images from George Dvorsky to show you. So the golden ratio is all about the Fibonacci sequence, which is a sequence that repeats over and over and over in nature, as it's an ideal ratio for strength to weight. And more, each number is the sum of the two numbers that precede it. And it would appear to be a kind of inbuilt numbering system to the cosmos. We intuitively use the ratio in art and design all the time, but could we use it to deliberately improve engineering? I say yes, that we need to rethink how we build man-made things. And I believe that using biomimicry as an engineering approach to problem solving is critical for solving some of the big issues we face. The way we've applied engineering design to date has been to plunder resources to meet our needs. For example, we mine ore, convert it into steel in factories, and make it into objects that we need, and then throw away most of it when we're done. This is not sustainable in the long term. These attitudes and behaviors are destroying our planet, and we need to have more respect for nature and solve problems in more natural ways. If we create using methods refined by nature over 40 billion years, it will cause less harm to our environment and help us to live in greater harmony with the natural world. Here to inspire you are a few of the top solutions that use biomimicry. Japan has some of the fastest trains in the world. They blast across the country at 300 kilometers per hour, taking passengers from Tokyo to Kyoto in just 140 minutes. This equates to the distance from Hammer Springs to Dunedin. Wouldn't it be useful to be able to traverse that distance in just over 2 hours? From Christchurch, you could almost visit the hot springs on your lunch break. Sounds great. But there was a problem when they developed the bullet train. When a typical round-nosed train passes through a tunnel at that speed, it creates a wall of air traveling at the same speed that releases a loud, cracking boom, disturbing wildlife and everyone in the vicinity. One of the train's engineers happened to be a bird watcher. He had observed the kingfisher diving into the water, barely creating a splash. By shaping the nose of the Shinkansen like a kingfisher, engineers were able to split the air instead of pushing it. This design adaptation eliminated the boom and gained up to 15% efficiency in the process. The shark is another creature whose attributes design engineers have copied to improve efficiency. The qualities of a shark's skin are inspiring. For example, you'll never see a shark with barnacles or other debris clinging to its surface. Sharks are also among the fastest swimmers in the ocean. This is a short-fin mako shark, and it's capable of speeds of up to 74 kilometers per hour. I'd like to point out that this is higher than the speed limit in most areas of Christchurch. What makes shark skin so fast is partly due to the skin characteristics. Their skin is composed of countless overlapping scales called denticles, literally meaning little teeth. The denticles have grooves that run down their length in the direction of water flow, which prevents eddies and swirls of turbulent water from forming. The grooves allow the water to pass over the surface faster. Here is some artificial shark skin. Swim coaches immediately saw the advantages of shark skin for their elite athletes. This is a very young Michael Phelps, whose races are won by fractions of seconds. And it worked. It worked so well that shark skin swimming suits have been banned in all major swimming competitions. However, it can be used other places. It's still used on the bottoms of boats. And we have learned that shark skin is antimicrobial. So it may offer great applications for surfaces in hospitals and on clinicians' and nurses' clothing. So back to our window washing example. What inspiration could we use from nature to help a robot climb glass and also be able to traverse obstacles? There's a little hint in the flyer for this presentation. As you may have guessed from the flyer, it's the Gecko. On my latest trip to warmer climes, I admired the way in which geckos could crawl along any surface, even over my head. They do so effortlessly and often remain upside down for hours. This characteristic ability is due to their super sticky feet and bulbous toes, which have microscopic hairs called setae. These setae are arranged at various angles and can snuggle down into the tiny nooks and crannies on a surface. They can move so close to a surface that molecular level electromagnetic attraction occurs. The gecko's feet are literally magnetically attached to the surface, which is amazing. So applying their knowledge of this phenomenon, researchers at Stanford University have created foot pads for humans that can be used to climb glass walls. Here are some examples of artificial setae and the adhesive tiles used by Stanford's design. And I have a short video to show you of that climbing the wall. This one has no sound. Do you notice he's not wearing any special clothing? He's just standing on that design. So it won't be long now before the first window washing robot climbs with hairy gecko feet. You can say you heard it here first. There's an opportunity to combine what we've learned from current robotic window washers with the biomimicry enhancements to accommodate the advantages of washing windows manually. This could include the ability to move past protrusions or obstacles and wash beneath overhangs. In the future, you may see a robotic Spider-Man rapidly scaling a tall building, scrubbing away as he goes. So I have a question for you of biomimicry in action. What's one thing people universally dislike about visiting their doctor? Having to visit them? Okay, beyond that, how do you feel about needles? I think we can all agree we hate needles. And if you don't hate needles, we're concerned about you. Needles for drawing blood, injecting vaccines, placing a catheter, they're all painful. We often continue to feel the pain in the affected area for some time afterwards. I remember walking the hall all night with my crying infant after her MMR shot. Nothing soothed her but my pacing. I can also recall a clinician making multiple attempts to inject me or to find a vein and not being able to find it, so trying a different site. People have experienced this, right? I'm not the only one. Okay. So it's no surprise that many of us dread needles. But imagine if you were a diabetic who had to jab themselves and test their insulin levels every day. Or a parent who had to test their child or carry an EpiPen, hoping they would never have to jab them. The phobias we have around needles are insignificant compared to what these people face. And thankfully, engineers are working on a solution. Good times. We can now make needle patch arrays in the form of an adhesive bandage. They contain thousands of microscopic needles that are based on the design of a mosquito stinger. So it's a good thing to come from a mosquito, right? The needles can't be felt. The microneedle arrays create a pathway for a drug to permeate the dermal tissue below the skin. And a pouch above the bandage can contain the drug and deliver it slowly over the period of a few hours or days, without causing any needle pain. Although there may be pain resulting from the contents of the pouch, I can't do anything about that, but this technology is referred to, this fabrication technology is referred to as microelectrical mechanical systems, or MIMS. It uses integrated circuit chip silicon wafer fabrication methods to etch mechanical devices. And a single wafer can contain hundreds or even thousands of MIMS devices, such as a needle patch array. Little fun there. Okay. MIMS devices can also be active sensors. They can measure the insulin levels in the blood and direct an implanted insulin pump to provide more insulin to the body. This means that a diabetic can be freed from monitoring their own levels by using a needle prick on their skin. This patch on the abdomen communicates through the wire to the reading pump there, but it can also be a wireless refillable pump. Another interesting idea is to use a MIMS hydrogel needle array that relies on osmosis to control the levels of insulin. When insulin levels are low, more insulin will permeate across the hydrogel membrane and into the body. And I have a short video to show you on this one.
This microneedle array patch is composed of a boronate-containing hydrogel, semi-interpenetrated by biocompatible and mechanically robust self-fiber derived from silkworm cocoons. The boronate hydrogel contained in the microneedles allows glucose-responsive diffusion control of insulin synchronized with the change in hydration on the gel surface, known as skin layer formation. The crystalline self-fiber enhances the mechanical strength of the microneedles to facilitate skin penetration.
The most remarkable advantage of this technology is that it is remarkably stable while providing both fast and long-acting glucose response to insulin delivery. It can overcome the limitations associated with current technologies such as short duration of action, instability, and plasticity.
One final example of biomimicry is sculptural, creating a better backpack. All backpacks look about the same. From those used by early mountain climbers to modern cyclists, they feature a top or front-loading design with various smaller accessory pockets, and these compartments usually feature a zipper or a drawstring. Backpacks are so ubiquitous, now we barely notice them. So raise your hand if you own a backpack. Pretty much everyone. But does a backpack have to look like these examples? They're very functional, but could we look to nature for a better design? How about an armadillo? Or its cousin, the pangolin? With their overlapping scales and armored hides, they are able to protect their innards from heat, injury, and of course the elements. and they're cute. A designer has actually used the penguin as inspiration for an entirely different looking backpack. These cute little guys, by the way, are famous for being the most smuggled creature in the world. It's kind of sad. So the pack opens up to be completely out of the way, allowing easy access to the contents. There are no zippers or drawstrings required. And unlike traditional backpacks, this design has hemispherical ring segments that can be made from rugged materials such as leather. Plus, it's stylish, waterproof, and can be made from recycled materials, such as the one of their current models that is made from inner tubes of tires. And you'll love this video. It's very good. Now let's take biomimicry a step further and allow the design to be dictated by nature itself. Instead of copying great ideas found in organisms, what if we let the organism be the designer? It's a cool idea. Airbus AP Works in Germany is doing just that. And I had the opportunity to interview manager Angela Grunwald about the Light Rider electric motorcycle. Weighing in at only 35 kilograms, even I could pick it up off the ground. This extremely lightweight bike can go from 0 to 80 kilometers per hour in mere seconds. This is barely faster than a Mako Shark, but it's definitely more suitable for riding. And it is powered by a 6 kilowatt electric motor. Water lilies served as the organic inspiration for the structure of the frame. Look at how beautiful this membrane-like structure is. The unique part of the bike is the frame, which is 3D printed from a metal alloy and weighs only 6 kilograms. 3D printing, which is also known as additive manufacturing, is done by depositing one thin layer of material at a time on a platter, and then you lower the platter and on the table, and you deposit a second layer. Okay? This process is repeated layer after layer until the final image emerges. Like this time-lapse video of the skull being printed. We're going to see it in a few seconds of duration, but it actually took 20 hours to print. The designers used an algorithm that allowed for natural growth of structures and patterns to obtain the lightweight organic shape. They began with a solid CAD model as shown, then allowed the computer to sculpt away the material that is excess for supporting the loads. And this model is then optimized and smoothed out to be aesthetically pleasing. They then 3D printed it using an aluminum powder alloy developed for aircraft parts. Due to the size limitations of their printer, they had to segment the motorcycle frame and then weld it together afterwards. I like it. I think it gives it a gnarled, calloused, kind of tree branch look. One of New Zealand's most famous artists, who was inspired by both nature and engineering, was Lynn Lai. He was born in Christchurch in 1901. Lai achieved international acclaim for designs that used natural force inputs, such as light, wind, and water, to create what he called experiential sculptures that would behave differently with different inputs. They make eerie, kinetic noises that are unique. And here are a couple of examples from the Lynn Lai Center in New Plymouth. Same place as the chimneys. Now you have to go. I'd share more, but we're running out of time. So I'm going to speed things up here. This is the water whirler. I'm sure many of you have heard about its demise. Yeah. It's an inexcusable tragedy, but not one that Lai was unfamiliar with. He was an artist, not an engineer, which meant he had problems with scaling up his designs as well. And as they grew in scale, their own mass made them prone to breaking. Predicting how materials would behave with the increased stiffness also proved challenging. Following Lynn Lai's death in 1980, many have tried to create larger scale versions of his designs. The University of Canterbury's mechanical engineering professor, Dr. Shane Gooch, has taken up the challenge and constructed several of Lai's designs, including this one called the Snake God and Snake Goddess. I have a short video of it, but I'm going to skip it. It looks like that, and it's very cool. Look it up online. I too have had my challenges scaling up a design from a desktop model to full scale. After working at NASA Ames Research Center, where I designed support equipment for life science experiments in the wind tunnels and on the space shuttle, I worked for 18 months as a design engineer for Sarcos Research Corporation in Utah. Our project was to design robotic dinosaurs for the Jurassic Park ride at Universal Studios Hollywood. And during my time there, I worked on 4 of around a dozen dinosaurs, which was a very fun project. We used biomimicry in yet a third way. to recreate the natural movements of creatures that lived between 200 and 145 million years ago. I designed the heads and jaws of the ultrasaurs as well as the nicks that were a team effort. And one of the dinosaurs that I worked on a lot was this one, the Parasaurolophus, which we called the Parasaur for short. Its name, the near-crested lizard, is derived from the prominent bone on its forehead. The dinosaur was an herbivore. As you can see by the picture, its head structure resembles that of a modern-day horse, which is different from we humans, who have an L-shaped jaw situated in the midline of our skull. Taking my cue from the horse's anatomy, I designed the Parasaur's jaw to hinge from the rear to achieve greater realism. The Jurassic Park ride is a water ride with rafts, each of which holds up to 20 people. You enter the ride through 2 large wooden gates and immediately see a mother and baby ultrasaur grazing on water grasses. I'll get back to these in a minute. For now, imagine you're cruising along the river enjoying arguably cute dinosaurs until suddenly a parasaur pops out of the water and knocks your raft off course and into the damaged building. Velociraptors and a T-Rex attack your raft before plunging you off a very real, very scary 26-meter drop. The first time I rode the ride on opening day, the dinosaurs didn't activate. So they insisted I go through again, which meant I got to scream through that drop twice. Later, I read that Steven Spielberg rode the ride on opening day too. But he got off just prior to the drop and walked back. Really? I mean, that was an option? My job was to make the Parasaur lunge out of the water rapidly. It was a 7-meter tall structure, rigid except for its mouth, and it had an enormous head bone. This meant it had to displace a vast amount of water. Unlike the Shinkansen, however, I didn't have the option of facing its snout up and reimagining a kingfisher. So instead, I had a massive hydraulic ram encased in an equally massive box beam steel frame. It took considerable computer analysis to design a structure that would withstand the repeated loading of a raft being knocked off course every couple of minutes for 12 hours a day. But I persevered on my little 21-inch monitor until it was ready. When I went to the fabrication facility to inspect the welds on the frame, I asked where it was, and they said, "You're standing inside it." It was only then that I realized just how tall 7 meters is. At least a 2-story building in height. This is some of the robotics inside of the Parasaur. Another challenge involved with recreating the Parasaur and all of the other dinosaurs was figuring out how to fit a rectangular geometric shape into an organic life form. The engineers had been working completely separately from the designers fabricating the rubber skins. We engineers had only these little sculptured maquettes to use as reference. It was difficult to build a robotic structure that translated well between a 30-centimeter tall maquette and a 7-meter high dinosaur, so I took it upon myself to solve the problem. Using a 3D laser scanner, I mounted my maquette on a rotating platform. The 3 lasers would scan rings of surface geometry and step up the structure to capture another ring of surface profile. I then hacked into the CAD software to figure out how the software read in datum curves. I used what I learned to write a small computer code to convert my scanner data into that format. And then I used the surfacing function in the CAD software to recreate a skin over the rings to represent the envelope of the dinosaur. And then I scaled it up to full size. We learned all kinds of things from adding the skin envelopes to our robot innards. First and foremost, organic life forms are made of ellipses. Take a cross-section through any life form, including myself, and you'll get an ellipse from my head to my neck to my torso, or a bunch of ellipses. But we like to design in rectangles. And since all of our building materials tend to come in rectangular geometries, that's a problem. It's the classic square in a round hole, except with ovals. For the fatter dinosaurs like the Stegosaurus, everything was fine. But the long, slender necks of the mother and baby Ultrasaur, it was a disaster of sharp metal corners. The mother's neck was nearly 20 meters long. It was composed of about 10 plate steel welded box structures pinned together with steel pins the diameter of a coffee mug or larger. When we printed out the neck linkages full scale and laid them end to end across the conference table, they spilled all the way across the floor and out the door. So we redesigned, eliminating as many high points as we could and changing the articulation points to give a more natural look to the movement. But our troubles were far from over. We delivered the components to the fabrication facility and they were assembled. But when they tried to put on the rubber skins, they didn't fit. It turns out that designers aren't engineers. Unlike engineers, they hadn't used the maquettes as scale models. They'd seen them as merely guidelines. This meant they made full-size skins that only roughly approximated what we engineers had been relying upon as the gospel truth. There was no time or budget to redo either the structures or the skins, so a lot of grinding took place. And the skins were shifted around to fit differently than had been intended, although I think they still look great. All the full-scale dinosaurs were made from foam and then coated with a clay using a sprayer. A designer would then sculpt the clay and add details by hand. The structure was allowed to harden. It was then used as a mold casting for the rubber silicone skins. The skins were all made of rubbers in large sheets, but the material properties of each were different to accommodate the different species, such as the armored plating on the Stegosaurus. And I have a video, fast-forward video of the T-Rex being sculpted, but we don't have time. Sorry. No one knows if the dinosaurs were warm-blooded or cold-blooded, but current thinking is that they were warm-blooded, based upon their bone cross-sections and thermal mass. We also don't know if they were drab brown or colorful, and whether their skin was feathered or knobby. As no one knows for sure, we took artistic license and gave the dinosaurs brighter coloration and skin texture extrapolated from reptiles. So this is the baby Stegosaurus, this is the maquette, and that's the little guy right there. The Ultrasaurs presented an additional challenge because of the length of the neck and the need to be upright. It also had to be capable of bowing down over the raft to munch on water grasses. The long silicone rubber skins were too soft and flexible, yet extremely heavy. They resembled a bad turtleneck sweater. So we added fiberglass tubes from the body to the head all around the neck. These tubes provided a support structure to secure the skin. They also gave the necks a more natural-looking motion in comparison with relying on just the robotic actuators between the linkages. Not all our challenges for the Jurassic Park ride were the dinosaurs. We were under enormous pressure to have everything installed and ready for Memorial Day weekend, which is the last Monday in May in the US, but we didn't make it. Instead, we opened on the 21st of June, 1996. Several of my colleagues lived in a hotel at the theme park for months leading up to the opening, dealing with unforeseen issues such as the design of the building that housed the T-Rexes. The building was 10 stories tall, And the T-Rex was directly above the drop, all roaring mouth full of teeth, swinging side to side with arms and legs reaching for you as they sprang into view. This is when they snapped that souvenir picture. You should see the expression on my face. The construction teams that made the building underestimated the size and weight of the T-Rex. When it swung its head from side to side, the entire building began to shake. It's exciting. The contractors probably predictably panicked and wanted to add beams to stiffen the structure, but our team saved the day by explaining the concept of resonant frequencies. Every structure has frequencies at which it readily vibrates, like a child on a swing or a paddle with a ball tied to it. If you're not exciting the structure at that frequency, it won't vibrate. The resonance issue disappeared when we altered the swing timing of the T-Rex's head. So I've enjoyed our journey down memory lane, remembering a time when I created dinosaurs for a living. Engineering can be used to solve many types of problems, and I hope I've demonstrated that not all engineers are human. Many of our best inspirations come from nature. We've made trains faster and quieter by configuring them like birds. We've increased swimmer and boat speeds with shark skin technology. And we've designed Gecko-inspired footpads that allow humans to scale glass walls like Spider-Man. And we've even let nature take the reins to design its own structures for human use, recreating dinosaurs to entertain and amaze us 145 million years after they walked this earth. Thank you. So I know it's 8 o'clock, so if you have to go, I will not be offended, but I'm happy to stay and answer questions for those that have some time. So. Some of you young men in the first row here. Yes.
I had a question about the shark skin.
Yes.
You said that it had antimicrobial properties.
Yes.
And the way it was framed made it sound to me like it was a geometric property of the skin rather than some sort of material property.
That's correct.
How?
I know, it's amazing. MEMS technology is so small that you can actually have these needle patch arrays where a water molecule is too large in diameter to fall between the needles. And therefore it rolls across the top and it's a completely hydrophobic surface. And so nothing will absorb. So therefore bacteria can't stick to it. Yes? Speak into the mic.
On your first time with dinosaurs, if they didn't activate, the Parasaur wouldn't have activated. So your raft shouldn't have gone off course into the building.
You are correct. But see, this is Hollywood. So the raft goes off course whether the dinosaur activates or not. Yeah. Yeah. It's a nice trick. So.
You were saying before with the how dogs could regrow their meniscus if it was like torn or damaged. Would it be possible to use processes like gene editing, like CRISPR, to have that sort of, and like stem cells to have that sort of situation put into humans?
Yes, I think that you're right on track there. That genetic engineering is a brave new world for us. There are so many things that we can do. We first have to study how the genes are working in the dog meniscus. Once we understand that, then we can try to alter the sequence using CRISPR or other technologies to see if we can get human meniscus to change. The caveat on that, and I hope that you'll take it into consideration, is like Jurassic Park, you know, anything that can go wrong will go wrong. So you might think, I've created all these dinosaurs so that they can't reproduce, but nature finds a way. Right? So.
You've been talking about biomimicry as taking the idealized forms in nature and transferring them to engineering projects. Are there any forms in nature which haven't transferred very well in an engineering context? Might be quite hard to think of an example.
There's a lot of examples. The thing is with how research gets published, it's only the successful stuff that we hear about. But I know that we're trying on many different fronts. And one of the ones that we've been working on for a long time is cartilage. And we can't get artificial cartilage to adhere to the bone because bone and cartilage are actually the same material. Our bodies start changing the properties of it as it approaches the surface of the bone. And we can't get something else to glue on there, so we've given up. We're back to total knee replacements. Yes, back there.
With the electric motorcycles, since they're super light, does that mean that if they swing along the road, they'll bounce around?
Yeah, I mean, the lighter something is, typically the faster you can go and the more fuel you save, but you're also less safe if you crash at that speed. You know, you don't have anything to really protect you. Motorcycles are that way, whether they're heavy or light, because you're on the outside of the vehicle. But it might be an advantage, because a heavy motorcycle, if you were to fall over and the bike landed on you, it might break something, whereas a really lightweight one wouldn't.
I was just going to comment, a good example of a failed biomimicry experiment might be using wings for artificial flight.
Yes.
Clapping
Yes.
wings, I should say.
Yes.
I had another question. This is a bit of tangential, but as an engineer developing sort of innovative solutions, there's always fear that the first place they'll turn up is on battlefields. Do you have any kind of perspective on that, or
They'll turn up where?
on battlefields?
Oh, yeah. I think that's unavoidable. Anything that's used for good can be used for ill. And the Department of Defense sponsors a lot of this research because they want it to work for them. Like those little cockroaches, they're real. They're sponsored by the military in order to spy on people. They've also made winged versions of those that each one has a small camera, but they can swarm and get a bigger image. If you've read Michael Crichton's Prey, it's where that technology goes wrong. But they're starting to do that, and I met with some people over at the Wireless Research Center a month or two ago, and they were talking about swarming drones for things. And yeah, I had that image from Prey coming back in my head. So. All right, well, I'm going to have to let you go, but thank you all for coming. Appreciate it.